All right, good afternoon, everyone. I'll let everyone kind of get settled here. So welcome to the afternoon portion of the Amygdala conference here. And I heard from Dr. Eric Meyer, who's my CME czar. He just wanted to put out a reminder, and I will also mention this towards the end, but for the individuals, I think would be psychologists and social work that would like to receive professional credits through PESI or BAMC, you need to sign in and make sure you hit all of those necessary wickets to receive a credit for today's conference. Okay? Yes, out in the front, out on the table, ma'am. I don't think you will need to. I think you are. So okay. Well, excellent. So without further ado, we'll start with the afternoon portion. And unfortunately, we had Dr. Jessica Gill of NIH. We had her billed, and you will see her in her biography in the program. She was unable to meet or be with us today because of a family emergency in Oregon. So have her in your thoughts, and hopefully things are going well. But not to be understated, we have someone in her postdoctoral fellow, Cassandra, I got to make this right, Pattison, who can speak about the subject matter here and works within the lab. Dr. Pattison is a postdoctoral fellow that works with Dr. Gill in this area of specialty. So, Dr. Pattison?
Hello, can everyone hear? Yeah, okay, great. All right, so good afternoon, everybody. Today I am presenting on behalf of Dr. Gill and our lab at the NIH. Much of our work is focused on traumatic brain injury and really looking at biomarkers that inform recovery and really looking at who and who does not recover following traumatic brain injury. But all of this work was actually started by Dr. Gill's interest in PTSD. And so I'm going to focus today on how our research kind of combines those two areas. I'm going to present 3 different studies that we're using in military populations currently. And each of these 3 studies are super preliminary data, so nothing published as yet. So if we can refrain from taking too many photos, that'd be amazing. But I hope that at the end of today, you'll kind of get a glimpse of some of the breadth of the investigations that we're doing in our lab and undertaking to investigate biomarkers that predict symptoms and recovery trajectories from peripheral proteins through to central mechanisms and gene activity. So all of which are potential stepping stones to improve outcomes following traumatic brain injury and for those who suffer from PTSD. So why military? Well, we all know that traumatic brain injury is a signature injury of the Afghanistan and Iraq wars. And we also know that the majority of these injuries being sustained are mild in nature. So many are recovering within days to weeks, but we do have quite a few that sustain that injury and chronic symptoms for years afterwards. PTSD, as I can see from the amount of posters outside, we do know that PTSD is really prevalent in military populations and veterans, so it's really important to study. So TBI and PTSD commonly co-occur, and their symptoms are very overlapping, and it can make it really hard to distinguish what's causing what symptom. That's kind of where we're coming in to see if we can find biomarkers to differentiate what's happening and really look at individual variability. So in the Gill lab, our whole focus is to really identify individual variability through gene expression, through proteomics, and through phenotypes. So that brings us to our first study, which is looking at does mild TBI with concurrent PTSD symptoms affect gene expression. And we're approaching this study through RNA sequencing. And there's also a very beautiful poster out there by Heather Rush if you have any questions about the data of this one. So we have 202 military personnel in this study. They came to the Madigan Army Medical Center. All of these people had been deployed within the previous 16 months, had come back from deployment. 64% had 1 to 2 TBIs and 24% had more than 3. So they came in, and what they did was they were given 6 weeks and up to 10 sessions of CBT, or cognitive behavioral therapy. So we took blood pre and post cognitive behavioral therapy intervention, and we ran RNA-seq analysis. And we also, following RNA-seq, we did IPA analysis, which is ingenuity pathway analysis. And so this is one of a multitude of tools out there that allows you to work with Amygdala, because it's really large, big data. And what it does, it allows us to identify the most relevant signaling and metabolic networks, molecular networks, and biological functions for the list of genes that we come up with. And the PTSD was measured using the PCL-C, and 35% of the participants were classified as having PTSD. So we first examined differential gene expression in participants with PTSD versus controls. And what we found was that there were 98 differentially regulated genes, and the majority of these genes actually correlated with the NF-kappa B network being dysregulated in PTSD compared to controls. So NF-kappa B is also nuclear factor kappa light chain enhancer for activated B cells, if you're wondering. And it's a protein complex that controls transcription of DNA, cytokine production, and cell survival. So NF-kappa B really plays a significant role in immune regulation, which is quite interesting following PTSD and something that we're kind of really focusing on in our analyses. And as you may be aware, the PCL-C can be broken into 4 symptom clusters. So that includes intrusion, avoidance, hyperarousal, and negative mood. So we dichotomized each of these clusters into high versus low according to the participants' responses. And what we found was that intrusion symptoms had a lot of gene activity going on, with 1,400 genes differentially expressed. And again, they were associated with networks of inflammation. And most of the genes were upregulated, as you can see in red. So this was all pre-CBT intervention. So after 6 weeks of CBT, we found that participants who had a clinically significant reduction in PTSD, which was 10 points on the PCL, they had 20 genes that actually became downregulated associated with inflammation. So we're actually seeing a decrease in inflammation gene activity. So, and again, with NF-kappa B being really important. So, super exciting preliminary work, and it's showing that inflammation is related to PTSD, and if we reduce PTSD symptoms, we can actually reduce inflammation, which is really exciting. And what also is really interesting is that the PTSD symptom clusters may impact gene activity differently. And so that comes in really handy when you're kind of treating people. If we know what kind of clusters that they're really high on and that kind of thing, it can really inform our treatment going forward. And intrusion symptoms seem to be the most influential on gene activity. So one of the things that I'm really interested in, and something that we started thinking about, was how sleep disturbances are involved, because we know that sleep disturbances are a common consequence of both traumatic brain injury and PTSD. So indeed, as we heard this morning, sleep disturbances themselves put people more at risk of traumatic brain injuries, and also increase the risk of developing PTSD following TBI. So obviously a really important thing. So we know now that TBI and PTSD are associated with gene expression, so we want to know, is sleep involved? So I know Dr. Gawain gave us an amazing overview this morning, so I'll go over it quickly. But I think sleep is one of the most important things that we can do for ourselves. It affects, if we don't get enough, we don't feel right. So it affects our physical health, our mental acuity, and our emotional abilities. And importantly, it's associated with our metabolic hormones. So we have increased insulin resistance, leptin and ghrelin, which are metabolic hormones that control our hunger and satiety. And it also influences our glucose tolerance. And obviously, with prolonged chronic sleep deprivation, we do see an increase in obesity. And finally, as we heard previously, sleep is important for clearance of the lymphatic system. So as we're sleeping, we're getting rid of proteins such as tau. So if we really are disrupting those sleep processes, we could be seeing an accumulation of tau, which is what preliminary data is showing. And we already heard that sleep in the military is super problematic. So in the field, there are things like safety concerns. There's a lot of shift work that happens. There's overcrowding in the sleeping areas. And we've really got to worry about how much temperature, like the temperature changes and the noise that's associated with those kind of sleeping environments. And for anyone who attends the CNRM retreats, every year we hear from some retired Army personnel, and pretty much every single time they mention how much their sleep is affected both in deployment and then post their TBI. So it's a really significant problem. Following traumatic brain injury, there is an increase in sleep disturbances such as insomnia, post-traumatic hypersomnia, and sleep apnea. We do see a small increase in the incidence of narcolepsy, although that's kind of associated with higher severity in traumatic brain injury. And we don't really know the prevalence of circadian sleep-wake disorders because, one, they're kind of hard to measure, and clinically, we don't really see them a lot being diagnosed in the doctor's offices. So this brings us to the Gill Lab's kind of one of our biggest philosophies and drivers is what biomarkers shape the development and maintenance of chronic symptoms such as PTSD, and what is the role of sleep. And talking about those overlapping symptoms again, number 1 and 2 are fatigue and insomnia. So from our lab, so this is some published data for you, we do know that PTSD and depression increase IL-6 concentrations, and then that's also associated with declines in health-related quality of life. And what we already have shown is that improving sleep relates to reductions in PTSD and depression, improvements in overall quality of life, and reductions in cytokine concentrations such as CRP and IL-6. So with our collaborators here at NICO and Walter Reed, we were able to obtain data for 107 service members and veterans. They were majority male and white and around 34 years. So this population was approximately 3 to 121 months post-injury, so fairly recent. And we were able to categorize these people into 3 groups based on their mTBI status and their PTSD status. So mTBI was done by a clinical interview, and PTSD was assessed by the PCL. And we used the DSM criteria of moderate to severe PTSD. So we have injured controls. So these people had been vetted they did present at Walter Reed, but they did not have a traumatic brain injury, and they didn't have any PTSD. Then we have the mTBI and PTSD absent group and the mTBI PTSD present group. We did have a injured control with PTSD group, but there was only about 3 people in there, so we can't include them in this analysis. So tau was measured by peripheral blood using Simoa, which is a ultra-sensitive technology, and compared across the groups. So one of the really cool things about this sample is that we don't have any differences in age, and a lot of the same kind of race and service branch kind of factors that come into play in a lot of our other samples aren't here in this sample, which is really cool. And this may look familiar if you've seen our poster outside. But we ran an ANOVA and we found that tau was highest in our participants with mTBI and PTSD present. And this was significantly higher than both the mTBI and PTSD absent and the injured controlled with PTSD absent groups. So that was really interesting, and we thought, we should really be looking into this further and seeing what is actually influencing this tau concentrations. So we ran purposeful selection method by Bersic, and what we found was that sleep medications and gender was associated with tau. So we included that in a regression model to assess whether TBI and PTSD independently contribute to tau concentrations. So what we found was that PTSD, the presence of PTSD, was associated with higher tau concentrations, but mild traumatic brain injury was not associated with tau. And interestingly, to kind of keep on with the sleep kind of realm of it, is that we found that sleep medications were associated with tau concentrations. So what this actually means, it's a negative correlation, so it meant that people who were taking sleep medications actually had higher tau concentrations. So, taking sleep medications had lower tau. And so, so what we were thinking is maybe sleep medications are actually helping with the glymphatic system and clearance. But we can't actually say that because we can't actually measure the people who aren't taking sleep medication to check their kind of sleep to see if it was disrupted. So that really made us think that, sleep may be an important factor, and we really need to start looking at that when we're assessing PTSD in these patients. So that ended up with this study, which we were able to think about sleep a little bit more and how it affects our gene expression. And so we have 107 military personnel. They were actually recruited from advertisements, but they came to either Fort Belvoir Community Hospital or Walter Reed for data collection. And we assessed PTSD using the PCLC again, and we looked at sleepiness using the Epworth Sleepiness Scale. So we have, again, a large sample of majority of white males, and of the participants that had TBI in this population, about 90%, 94% were mild in severity. So we were able to get 3 groups again. So we had PTSD with sleepiness, PTSD without sleepiness, and no PTSD and no sleepiness. So obviously we had no PTSD and sleepiness was only an N of 4, so we couldn't include that in our analysis again. So we performed RNA-seq analysis, again, in parens, and each sample had at least 30 million reads. And here we report differentially expressed genes with a false discovery cutoff rate of 0.10. So what we found in the sleep PTSD versus controls, we had 251 genes dysregulated. In the sleep PTSD versus no sleep PTSD group, we had 1,873 genes dysregulated in this network. And so, as you can see here, it kind of looks like that sleep is maybe really this driving force on what's happening in these gene changes. It might not necessarily be due to PTSD or TBI alone. So we ran the IPA analysis again, and I'm just presenting the top networks here. Again, this is super preliminary. So for the sleep PTSD versus controls, our top network was associated with organismal injury and abnormalities. So key genes in this network have been associated with immune response, neurodegeneration, neuroinflammation, aging, some with circadian rhythms, which is really cool. And really interestingly for us is that a lot of these genes have been associated with insulin sensitivity and metabolism, which really shows that kind of link to sleep and the fact that these sleep disturbances may be really affecting our genes at this level. So in the sleep PTSD versus no sleep PTSD comparison, our top network is associated with RNA post-transcriptional modification, connective tissue disorders. So again, genes in this network have been correlated with growth hormone deficiency, neurodegeneration and inflammation, aging, circadian rhythms, mood disorders and fatigue. And really interesting is that this mitochondrial function keeps coming up in the networks here. And we know that mitochondrial function actually really is key driver of fatigue in multiple other conditions such as cancer, multiple sclerosis, chronic fatigue syndrome. So this is a really interesting link that we think we would really like to explore further. And finally, 3 of the genes in this network are actually associated with insomnia and Chinese fatal familial insomnia. So that is a really very rare genetic disorder where basically insomnia starts off quite mild and then it progresses to be quite advanced, and it really affects cognitive abilities and general health and well-being of these people that have this syndrome, and it can lead to death in some rare cases. So that's really interesting. And so to kind of really paint this mitochondrial picture, the IPA gives us some top upstream regulators that they think are important to our networks. And it's really interesting that there's 3 bottom ones all relate to mitochondrial function. So that really does point a picture that this sleep kind of might be really driving some significant problems for these people. And if anyone is doing some mice models and they want to do some knockout genes, come chat to us. We'd love to validate. So yeah, but we're still in the process of kind of doing this analysis, as I said. So as mentioned, very preliminary data, but it appears that sleep may be an important factor which impacts on gene dysregulation above and beyond PTSD and TBI alone. Given our current understanding and the work we're doing in the field, it is vital that we continue to measure sleep in these patients with PTSD and or TBI. And I think that that's how we're going to make some significant leaps in treatment in future. So the third and final study that I'm going to talk about today is we're looking at TBI and PTSD and having a closer look at central mechanisms, including exosomes and microRNA. So we have been working with the team at Sensi and Dr. Kim Kenny. And really, Dr. Gill and Dr. Kenny have been trying to kind of go beyond the current science of TBI and really find out what's going on with these late life outcomes and neurodegeneration and work out which service members are most susceptible to the effects long term and how we can improve treatment. So one strategy to do this has been developed in our lab over the last couple of years, and it's basically using exosomes, which are extracellular vesicles that can be transported across the blood-brain barrier. So they're available in peripheral blood. It's just a blood sample taken normally, and we use antibodies, specific antibodies, to pull them down out of the blood, and we're able to work out if it's neuronally derived or if it's just like kind of central, and you can use other antibodies to find out if it's from the liver and that kind of thing. So this is really exciting work. And so what this is looking at is with the Sensi data, we've got 3 groups. So we have people with no history of TBI, 1 to 2 TBIs, and repetitive TBIs. And I think one thing to really note is that this is a really very chronic cohort where we've got 11 years post last injury to 7 years post injury is our average. So a really interesting thing. So this is another published study, so that's exciting. And what this is really showing is that there are significant differences in the amount of p-tau, in the amount of exosomal tau, and the amount of plasma tau in these repetitive TBI groups, trending towards significance in the peripheral plasma tau. And so the tau is higher in the repetitive TBIs compared to the 1 to 2 TBIs and the no TBI group. And what this kind of data is showing is that exosomes may provide a clearer picture, and it may be that for biomarker work we need to start looking at exosomes more frequently, especially in these more chronic cohorts that have been sustaining either 1 to 2 or repetitive TBIs. Okay. So from these exosomes, we actually extracted microRNA. And microRNA is a small non-coding RNA molecule. It is involved in RNA silencing and regulation of gene expression. So we have 137 samples, which is adequate for an analysis. We have 30 with repetitive TBIs, we have 64 with 1 to 2 TBIs, and 43 with no history of TBI. So we prepared RNA and we used a nanostring 800 miRNA panel for expression and analysis. So again, super preliminary, but we carried out a one-way ANOVA between groups, and we developed this heat map which shows several clusters. So on So on this axis, we're looking at the sample, sorry, and then on this one, we're looking at the gene. So obviously, super tiny and you can't read it, but the red is showing upregulated genes and the green is showing downregulated genes. So after that heat map was normalized, we found that there were significantly differentially expressed genes between the repetitive TBIs and the TBI negative group, and the 1 to 2 TBIs and TBI negative group. And there were 19 significant different probes identified that were differentially expressed between these groups, and that's listed in this table. And the 4 highlighted in green were actually shared between those two comparisons. So IPA analysis is conducted again here, and we can see that the top pathways that are associated here include immunological diseases, inflammation, and neurological diseases. So that's pretty interesting. And I also had a quick look at some of these probes and just to kind of get a handle on them. And the ones in green are all related to kind of inflammation. But then interestingly, this probe here is associated with autophagy, which is basically helps a cell survive a spectrum of stressful conditions, including starvation, growth factor deprivation, and misfolded protein accumulation. And so this probe is like kind of abnormalities in autophagy play a role in neurodegeneration and things like cancer. And this probe specifically has been shown to control autophagy by directly regulating intracellular levels of 2 key autophagy proteins, ATG-FILC and BECN1. So that is some super exciting data that we've found in this very preliminary analysis again. So unfortunately, we can't make any definitive conclusions at this point, but I think this data really does show that traumatic brain injuries do matter, and the change in expression can be seen in microRNA, and this can be years post-injury. And we do think that it's important that we start incorporating measures of exosomes to really try and improve our understanding of injury and biomarkers and outcomes in chronic samples. So in conclusion, today I think we just wanted to kind of highlight the multiple platforms that we're using at the moment to explore traumatic brain injury, PTSD, and sleep in this population. So we know that PTSD in military samples are highly correlated with TBI, and we have higher concentrations of inflammatory biomarkers following both. We need to continually assess sleep, and this is becoming more and more evident. And as Dr. Gill said this morning, we need to kind of really teach our doctors and kind of bring up our health system to kind of follow the same trends. And we also, if we reduce PTSD symptoms, we can reduce inflammation. So all of this work is in the hope to shed light on the interactions between genetics, epigenetics, and proteomics that underlie PTSD and TBI to improve the management, treatment, and outcomes following TBI. And so this work would not be possible without the amazing participants that we have across multiple studies, all of our incredible collaborators, and our amazing group at NIH. So thank you all for listening.